The control unit has now been completed. Now, as I mentioned in the last video, what I mean by completed is that it is now easily extendable. So if we want to add in any extra registers, we can do that without increasing the wiring too much within the control unit. And also if we want to increase the number of instructions and the complexity of the instructions, we can do that quite simply as well. So let's talk through some of the changes. The first thing that you're going to notice here is that the counter has only got 4 outputs. So in effect what we've done now is we've split the fetch and the execute phases. The fetch is a hardwired and the execute is controlled via the microcoded ROM. So the fetch is hardwired and the execute is microcode. Now there's only one exception to that, and that's the jump command. So the jump if command still is controlled by one point in this counter. Now I could have taken the jump if command and completely microcoded it, but when I did it, the actual design was more complicated than what we've got at the moment. And what we've got at the moment works perfectly well. Plus, if you go into the actual counter, we've still got all of the positions within the counter. It still counts all the way up, but we just don't take any of the outputs. Now, we only take outputs at step 1, 2 and 3, which is the fetch cycle, and also step 6, which we're going to use for the jump if command. Now we wanted to keep all of this as it is, because whenever the stop comes along for each of the, at the end of each block of micro instructions, we want to be able to stop it at any point along the entire length of this counter. So that's why I've left all of that in. And that's why as well I've decided just to leave the jump if command as it is, because we've still got all of the wiring within the counter here in order to do this. Also, you can call it a counter or a stepper, you know, whatever you want to call it, it's up to you. Now that's the first change. The second change is in a little like race condition that occurred due to this stop command. So what happens is the output here of the microcoded ROM heads into all the set and enable outputs. Whenever we get the end of a little block of micro instructions, so for example, here's a block of micro instructions here, right, which begins at 08200, 01004, and the stop command is then 00002. So this stop command heads out and it goes to the respective line here, which is this point here, and this is the stop, and the stop then heads up, if you can see that here. So the stop here, and the stop heads up and it goes into the counter and it stops it. It stops the execute phase, and then it resets it back to the beginning of the fetch phase, which is position 1 in this counter. But the problem is, whenever it does that, it jumps back to position 1. When it's jumped back to position 1, we're now in the execute phase. So instantly we get into we're now in the fetch phase. So instantly we get into that fetch phase. And whenever we do that, this line here is going to go low. And whenever the line goes low, it then therefore prevents any output coming from here. So it actually prevents this stop command actually coming out. So we've got a little race condition running around this loop. So I stuck in a little memory element. Okay, so it's just a 1-bit memory, and the 1-bit memory is controlled by the clock set here. That's just this clock set, and that clocks that information through. Okay, so it stops that race condition. So it puts a little block on it, and it stops that race condition occurring. So that's the first thing to. The second thing to note there. Now, as I mentioned in the last video, we wanted to be able to take the instruction set that we have. So in effect we've got an instruction set architecture, so which is basically just how we define the zeros and ones for our instruction set. So we decided that a 1000 is an add instruction. For example, 1001 is a, I can't remember, is it the next one I'd say an OR instruction, and then they worked its way up to an AND. So we've chosen that particular set of ones and zeros to define our instruction set. Now, our instruction set has to get mapped into the microcoded microcoded ROM. Now, the simplest way of doing it, and the way that we've done it, is we've just taken the actual instruction. So, for example, an add instruction, the opcode is 1000. So all it does is it goes to position 1000, and there's another couple of zeros at the least significant bits. Okay, so it goes 100000, so it goes to that position within the microcoded ROM, and when it gets to that position, it just pulls out the zeros and ones it needs here in order to produce all the sets and enables in order to provide the add instruction. So it meant that the position of our micro instructions, okay, so you could call each one of these outputs here, for example 08200, that would be a micro instruction. Okay, so the position of these micro instructions would just be dependent on whatever the code we chose for to represent our opcodes. So it meant that they would be positioned really just randomly all over the microcoded ROM, and we didn't want that. We want to position them so that they take up the minimum amount of space, and they leave as much space available to us in order for us to put in some more instructions. Okay, so that's what we've done here. Now, my initial thought was that we deal with this at the assembly stage. So we generate our machine code that we can load into our RAM, and that's a program. But then we also generate this microcode, which is different from the machine code. And the microcode, it's the machine code, but it's been then adjusted and changed so it fits into the micro-coded ROM in a much more efficient manner. But I decided against this because we're going to end up with two sets of, in effect, machine code which is going to be generated from the assembler. One is the existing machine code we've been using throughout the course to write our programs, and then there would be another one that you wouldn't actually see, but it would generate in the background, and then we would load that into the microcoded ROM. But Timothy Morgan came up with another idea here, and it's quite neat and tidy. So let's have a look at this. Now, the way it worked previously was we had our 4-bit opcode, and that 4-bit opcode would provide the starting address for the ROM. And then the offset addresses were given by this little counter. But what we can do is we can split this up. We can take the 4-bit opcode, and instead of that 4-bit opcode pointing to the starting position, we could take that 4-bit opcode, which is really just 16 positions, and we can take that and we can point it to a little ROM, and that little ROM can contain the starting position for our little section of microcode. So let's say, for example, we had an add instruction. The add instruction would be 1000, So that 1000 would now come in here. We would go to the position 1000, which is somewhere within these 16 bits. And this is going to give us the starting position for our add command. And this starting position now is going to be different from the opcode. And we're going to be able to choose this starting position. So we've got each of the starting positions here for each of our different instructions. Now, once we've provided the starting instruction, this start instruction comes out of here and goes into this little adder. And of course, after we've got the starting instructions, we still need to offset via the next instruction and the next one. So I should actually say the next micro instruction and then the next micro instruction. And again, we still do that with this little counter. So now the starting address is provided by here, and it's not dependent on what the opcode is. So it means we can position everything so that it is really tight within the ROM block. So if I was to open up this ROM block here, if I go edit and open it up, you can see that we've got all of our micro instructions here one after the other. And you can see whenever we get the end to the end of a micro instruction phase, because we're going to have the same command, which is the stop command, which is 0002. So we've got these two here, first of all 08200 and 01004, and these are two steps of our micro instructions, and the 00002 is the end. So in effect that's like our 4, 5 and 6. Okay, and then it goes on to our next one, which is another 4, 5 and then 6, and another 4, 5 and 6, and then a 7 would be the end, and so on and so forth. So it frees up all of this other available space, but it doesn't just free it up so that we can use just individual lines. We can place our code anywhere within this block, and we can use up every single position within this microcoded ROM. So it's a neat little way of compressing our it's really compressing our instruction set architecture, and it's compressing it into the microcoded ROM. Now finally, one other thing that I did here was I simplified the Reg A and Reg B enable, and also the Reg B set. Now there's not a whole lot done here that's different. It's just a bit of a simplification. So we took out the Reg B enable and the Reg A enable lines here, and instead of feeding them up along into the Reg A and Reg B here and making the choice, what we do is we take our 2x4 decoders, the same 2x4 decoders you would have seen up here in the previous example, and we've placed them down here, and then we've made the choice between them using these two lines, and this choice is going to determine whether we're going to have our Reg B enabled or Reg A enabled, and also the other option is Reg B set, and the Reg B set again is controlled via the other line here that comes in, which is this Reg B set line here. Okay, so there's not a whole lot of difference, it's just it tidies the whole thing up a little bit. So that's all of the changes that are made within this control unit, and the great thing is now is that if we want to expand this, you can see I've written down expansion and expansion. So if we want to add a number of registers, so we want instead of having 4 registers, we want 8, then we just grab everything here, okay, from this line, this position below, and we stretch it down, and then we can just add in extra registers here. Okay, so the extra register we just add in these positions for our enable and for our sets. Now if we want to increase the number of instructions? Well, we can increase the number of instructions. You'll notice here that I've already expanded the opcode out. So the opcode where it was 4 bits, I've added on another 2 bits. They're not actually doing anything at the moment, but they're just sitting there providing some space for us. So we've already got the functionality to add in a load more instructions, and also we can make these instructions as much as 16 phases. Okay, so if you like 16 enable set phases. So that's everything in the control unit. Let's head up to the top level and we'll just stick in a little quick program and we'll just show you it actually working. So I head up here. If I head into it's all reset. If I head into view motherboard, so again we've got the 40 and then the 8000, which points to the first address of our program. So let's say the first address was just, we're adding, we're going to put numbers in, so we'll do the data and we'll put in the number 1, and then we'll go 21 and we'll get the data number 2, and then 22 data is number 3, and 23 data is number 4, and we'll get the stop command. The stop command is 70. So we've got our ROM here, which in effect contains our BIOS, okay? But our BIOS is very simple. Our BIOS just says point to the first address of the program. The first address of the program is the first address of the RAM. But as we expand on this CPU, the BIOS will get larger, and in fact we'll actually add in microcoded programs into this ROM that we could go and fetch and drag out, okay? Now, but as it stands, it's just simple. So, and this is our RAM, and this is where we actually hold our programs. And this program is just going to put 1 in register 1, 2 in register 2, 3 in register 3, and 4 in register 4, and then it's going to stop. And we know that it's going to do this because we have ensured that, if we get into the control section, we've ensured that the ROM block here contains the start addresses of the new start addresses of our instructions for our micro-coded instructions, and we've actually got our micro-coded ROM here all filled out as well. So we're all ready to go. So I'll just actually click through these, okay? So we'll just go through one at a time, you'll see it happening. So we're going to take in the 40, which is telling us to jump to the address. The address is 8000, so it's telling us to go to the first line of the RAM of our program, where our program is. It pulls out the first instruction, which is 20, and then it goes through the execute phase of that, and it puts 1 in R0, and then it goes and it pulls out the next instruction, which is 21, which puts 2 in R1, and 22, which puts the value of 3 in R2, and then 4 in R3, and then it should light up in red whenever it grabs the end command. So that's the end command, which is 70, and you see it's ended. So I haven't tried it out in every instance, so I have to go through and really check all of the function out, make sure all the functionality does actually work. But ostensibly that's our control unit completed. Now what we want to be able to do now is expanding it, so we're going to do that by looking at and putting in a stack and a stack pointer. So we'll look at that next. Thank you for listening. I'll get you on the next video. Goodbye.